This is the second video for 18.1, looking more specifically at the acid-base calculations now that we can understand how the ionization of water works. So if we have a strong acid, strong base situation versus a weak acid, weak base situation, in which we'll look at a little bit later. But strong acid, strong base is a little bit easier in which to understand. Your pH and or pOH, depending on what you're looking for, can be deduced directly from the initial concentration because we assume that with a strong acid and strong base, you have full dissociation into its separate ions. Therefore, the initial concentration of your acid and or base is the same as the concentration of the equilibrium. So let's go through and calculate the pH of a strong base first. So looking at a strong base, if we are reacting 0.1 moles per decimeter cubed of NaOH, I write my reaction. NaOH directly dissociates into Na plus and OH minus. I put my ice table together, initial concentration, change in concentration, and equilibrium concentration. I know my initial concentration for NaOH is 0.10, and therefore my products are 0.00 and 0.00. We know we are going to see full dissociation. Therefore, we need to lose our entire reactant because it is reacting and breaking apart, which means we need to add that same amount to our products. We don't really care about the sodium, so I'm going to skip that because the hydroxide is what we actually measure. Therefore, we get a concentration of OH at 0.10. We are looking for the pH. So before I can calculate pH, I need to determine my pOH. So pOH is 10. To calculate the pOH, we need to use the negative log of our hydroxide concentration, which is 0.10. You get a value of 1. Therefore, we know 14 equals pH plus pOH. Therefore, 14 equals pH plus 1. Therefore, pH is 13. All you need to remember is how to use the concentration to calculate pOH, and the pH and pOH, or the water constant we talked about in the previous video, can be used to calculate the pH of the substance. That was an acid or base. Now let's look at this acid. We are reacting 0.15 moles per decimeter cubed of sulfuric acid. It is a strong acid, therefore we assume full dissociation. So H2SO4 dissociates into 2 hydrogen ions in order to balance it out, and 1 SO4 negative 2. We are starting with our initial concentration of 0.15. We assume full dissociation, therefore we're going to lose that entire area. So we want to add that to our products. Now, keep in mind, we have that coefficient of 2. So that means we're going to have twice the concentration of hydrogen ions as we originally started with, because it dissociates into 2 of them. I don't care about the sulfate ions as they are not measured by pH. Because I'm looking for pH, this is a much more simple calculation where we just do the negative log of the concentration of our hydrogen ions. When we go that calculation, we get 0.52, representing an incredibly strong acid. What happens when you have a weak acid or a base? Well, we know weak acids and bases do not fully dissociate within the water, and therefore they're going to reach an equilibrium point. That being said, we need to write an equilibrium expression. Looking at an acid first. A generic equation, HA plus H2O, gives us H3O plus, or what we consider our hydrogen ion, remember, and the anion to our acid, A minus. Our equilibrium expression is Kc equals our products over our reactants. Just like in the Kw constant or water constant calculation, water is assumed to be constant, as the initial concentration should be the same as the final concentration at 25 degrees Celsius. Therefore, we manipulate just like we did with our Kw, where we get Kc times water. That, because we're working with an acid specifically, now becomes a Ka. Therefore, Ka equals your hydrogen ions, or H3O plus, and your anion, A minus, over your acid. This is called the acid dissociation constant, or I call it your Ka, or your acid calculation. Same thing can be done for your base. So we have your base, and that reacts with water. You get your base with your hydrogen, so BH plus, whatever that happens to be, and you have your hydroxide group that is released. Following the same exact setup as before, but I skipped all that writing, water is a constant, so we do not need to worry about it. So we get Kc times the concentration of water, but because we're working with the base, we get Kb. Kb is equal to the concentration of BH plus times your concentration of hydroxide ions over the concentration of your starting base. This is called the base dissociation constant, or Kb, or your base equation. Now, the importance of your Ka and Kb values. Because we're working with weak acids and bases, we need to be able to compare their strengths because there's a variety of weak acids and a variety of weak bases, and they're going to have different strengths and have different purposes and different dangers and health issues associated with them. So being able to calculate your Ka and Kb allows us to compare the strengths of those acids or bases. We will need to calculate the ion concentration at equilibrium using your ICE table. You can then calculate your pH or your pOH depending if you have Ka or Kb. So be really careful that you're paying attention to the acid or base and the appropriate P or pOH in which you are supposed to use. We are going to be creating ICE tables again. So keep in mind when you're doing an ICE calculation that your given concentration is going to be the I, your initial concentration. Your pH, if given your pH, you can calculate your hydrogen ion. If you're given your pOH, you can calculate your hydroxide ion concentration. In all these calculations, you have small Ka and Kb values. Therefore, we assume that initial concentration for your acid or base is the same as the equilibrium concentration in which you're going to use. And you'll see no change. Alright, so let's do an example of what this can look like. On this particular example, we are going to be calculating the Ka from a pH and initial concentration. So we're looking for Ka. So when you have 0.01 moles per decimeter cubed of a weak acid, CH3COOH, and you have a pH of 3.4. Well, in setting up an ICE table, we know we need concentrations. And we need the concentration change, and we're not given a change, but we are given a pH value. So you know how much your weak acid dissociated due to the hydrogen ions accumulated. So the first thing I'm going to do is calculate your pH. So if you have pH of 3.4, you do 10 to the negative pH. Put in 3.4, and you get your concentration of 4.0 times 10 to the negative 4, not 14. I apologize. Now that we have that, we are going to set up our ICE table. To set up our ICE table, we need to write our reaction. So we have CH3, COOH. That dissociates into CH3, COO minus, and H plus. We know our initial concentration of our acid is 0.01. we know our final concentration we calculated from our pH to be 4.0 times 10 to the negative 4. Therefore, we now can go through and calculate everything else we need. We have 0 concentrations for our products. So I'm going to go ahead and put those in. We know the change in concentration to be 4.0 times 10 to the negative 4. I'll put that into each of those other spots. Remember, you subtract from your reactants. Quickly do your math. Now, this is an extremely small number, one that is really not able to be measured by our instruments. Therefore, we are working with this small Ka value, and our initial concentration of acid is roughly the same as our equilibrium concentration of our acid. So we're going to assume it stays the same. Now we need to set up our equilibrium expression. Our equilibrium expression is written from our reaction. So Ka equals our dissociated ions over the original acid. Input the values in which you calculated above, and because our two ions have the same calculation or same number, we can just square that value. Plug it into your calculator, and you get 1.60 times 10 to the negative 5 for your Ka. And so again, as we had mentioned, that Ka is incredibly small. It is not a pretty number, which is why we can calculate what's called a pKa to match like a pH or pOH. And that is discussed a little bit later in this lecture. What if you want to calculate the concentration of hydrogen ions and your pH when you're given a Ka value and an initial concentration? Just like before, we want to set up our reaction. Because we don't have a pH, we can't really do anything from there. Going through and setting up the reaction, we have our dissociation of CH3COO- and H+. Set up our ice table. We have our initial concentration of 0.05 moles per decimeter cubed of our weak acid. The rest of it stays the same, or stays 0.00. We do not know our change. We know a Ka value, but we do not know the change. So remember back in the last topic of topic 7, what we have to do. We have to set each value to x. So we have an unknown change. Alright, so we've set everything equal to x. Because we have an incredibly small Ka value, as we have determined above, that means our initial concentration of CH3COOH has not changed in a measurable amount. Therefore, we do not need to worry about the x in that term, and it will just be working with the 0.75. Now let's create our equilibrium expression. It is the same as in the previous slide. Input the information which we know. We know our Ka. Each of our products are x, therefore we're just going to make it x squared. And we know the value of our weak acid. Go through and you do the math, and you get the 1.8 times 10 to the negative 5 times 0.75, you get 1.35 times 10 to the negative 5 equals x squared. Take your square root, and you get your hydrogen concentration of 3.7 times 10 to the negative 3. That is your hydrogen concentration. That answers one part of the question. The other was pH. So if I know hydrogen concentration, I can calculate the pH by taking the negative log of that concentration. When I do that, you get 2.4. Now what if this was POH? If this happened to be a POH value, you then would have to take the equation of 14 equals pH plus POH to find that pH. Otherwise, everything else is the same, whether you're working with your Ka or Kb value. Now, as mentioned before, these Ka and Kb values are incredibly messy because we're working with something times 10 to the negative, very, very small values. Just like pH or hydrogen concentrations and hydroxide concentrations are very messy, and we created a pH and a POH scale, we've done the same thing with our Kas and Kbs. So we've created a pKa, which is the negative log of your Ka value, or your pKb is the negative log of your Kb value. So that is if you know your Ka and Kb concentrations and you're looking for your pKa or pKb. Keep in mind this is just like pH and POH. You are just comparing your Ka and Kb, which are the representatives of the strength of your weak acid or your weak base. That's all it is. If you know your pKa or your pKb and you want to find your Ka or Kb, you do 10 to the negative of that value. Just like in pH and POH, the values are positive and have no units. The relationship is inverse. So if you have a strong versus weak acid, a strong acid going from weak to strong, you increase the Ka value, which means you decrease your pKa value. If you're going from a strong acid to a weak acid, you're going to increase your pKa and decrease your Ka, just like you are doing with your hydrogen concentrations and pH values. They're inversely related. When you change one unit of your pKa or pKb, you have a tenfold increase in your Ka or Kb, just like you do with your pH. So a very small change in your weak or strong acid has a tenfold increase in the amount of dissociation that occurs. And because it is just like a Kw, Ka, Kb, we're using this funky little letter K, it works at specified temps. For different Ka and Kb values, you can reference Table 15 in your data booklet to see different Ka, Kb values for different weak acids and weak bases at appropriate temperatures. Alright, so how can we bring this all together? Well, if you think of your Ka as your hydrogen concentration in a weak acid, and you think of your Kb as a hydroxide concentration in your weak base, we know hydrogen concentration times hydroxide concentration can be set to your Kw. Therefore, your Ka and Kb values can also be set to your Kw. That means your pKa plus your pKb will equal your pKw. We know your pKw or your Kw is 1.00 times 10 to the negative 14. So when we take the negative log of that, you get 14 at 25 degrees Celsius. Therefore, your pKa plus pKb can equal 14, just like your pH and your POH. pH and POH tend to be used for strong acids and strong bases, but depending on what you're given in the problem, all the math is the same. It's just whether or not what variables you're putting in there. This whole situation holds constant for any conjugate acid-base pair in a weak acid, weak base situation. Keep in mind, if you increase your Ka, that means you're increasing the strength of your acid. Therefore, you're decreasing your Kb, so your conjugate base is going to be weak. And vice versa. Decrease your Ka, you have a weak acid, that will increase your Kb, which means you're making a much stronger conjugate base. And that will be talked about more in the next sections of the HL topic for acids and bases.